So now we need to address the nomenclature piece. How do we name these compounds, these stereoisomers, so that the names actually reflect the structures? So we do this using what is known as the Kohn-Ingold-Prelog system. And so we start with a molecule like this. So the way that this works is by doing the following. First step, assign priority to each atom at the chiral center on the basis of highest atomic number. So the higher the atomic number, the higher the priority is for the group. So our chiral center is this center right here. It's the carbon that is attached to 4 different groups. So what is the highest priority group here? Well, we have a hydrogen, a carbon, and an oxygen. Of those 4, oxygen has the highest atomic number, and so is our highest priority. Hydrogen is going to be our 4th priority because it's lowest atomic number. These other 2 atoms, though, are both carbons. And so how do we differentiate there? Well, what we then have to look at is what those carbons are attached to. So this carbon is attached to 3 hydrogens, whereas this carbon is attached to 2 hydrogens as well as another carbon. The 2 hydrogens are the carbon is higher priority, so that makes this, the ethyl group, higher priority than the methyl. So we've assigned priority. Second step, rotate the molecule. This is where your model kit will help you. So that number 4, or the lowest priority, points away from you. So again, this is a place where your model kit is very, very helpful to you. Why is that? Well, so for this case, I don't need it because the molecule is already pointing the correct direction. But if it's not, trying to rotate a 3-dimensional image in your head can be very, very difficult. But if you have a model kit that you can do it with, that becomes much easier. Again, I'm having some technical difficulties here, so I can't show it to you on camera. But you literally can take your molecule and rotate it so that that lowest priority group points away from you. Once you've done that, you'll draw an arrow that goes from highest priority to second priority to third priority. And then the name of the molecule, or the name of the chiral part of the molecule, is all based on the direction of that arrow. So in this case, the arrow is going clockwise. And we can kind of think of clockwise as going to the left. And if you know your Latin, the Latin word for right is rectus. And so this chiral center will be defined as R because the arrow is going to the right or clockwise. Now, if the arrow was going to the left or counterclockwise, we would use the Latin word for left, which is sinister, or we would call it S. So let's look at another example now. So here's an amino acid. This is alanine. So first question, where's our chiral center? And it's the only place in the molecule where we have a carbon that's bonded to 4 different groups. What is the 4th group, though? Because there's only 3 drawn in. So if there's only 3 drawn in, then we know that the 4th group has to be a hydrogen. Now, which direction is that hydrogen pointed in? Well, in this case, we already see 2 groups that are in the same plane. We see one that's pointed toward us and one that's pointed away from us. Or, I'm sorry. There's 2 in the plane, 1 pointing toward us, and that's it. But we know, in general, the way that we draw a carbon is that there's 2 in the plane, 1 toward and 1 away from us. So since the one that's missing here is what's pointing away from us, then we know that's the direction the hydrogen has to be. So again, we can assign priority. Nitrogen is higher priority than carbon because we're attached to a nitrogen here, carbon, carbon, and hydrogen. Hydrogen being the lowest atomic number is always going to be our lowest priority. When it comes to the carbons, though, this carbon here on the left is attached to 3 hydrogens. The carbon on the right is bonded to an oxygen and then double bonded to another oxygen. And when it's double bonded to an oxygen, we count that as being bonded to 2 oxygens as well. So since the first group it was attached to was the same, then we have to go to what that's attached to. And we can see that oxygen is higher priority than hydrogen. So we have 2 here and 3 here. So now we can draw our arrow. 1, 2, 3. That's going counterclockwise. And so we would define this as S. So what about the other isomer for alanine? What would it look like? Well, we would just need to invert the direction of one of the groups, which now gives us this molecule. The priorities are all still going to be the same. But now that hydrogen is pointing toward us. So what do we do to fix that? Well, this is when you would look at your model and you would rotate your molecule so that the hydrogen's pointing now away from you. And what that'll end up looking like after we do that is this. Again, this is something that your model kit will help you with greatly. So these are the same molecule, but I've rotated them using my model kit. You can see now our priority goes 1, 2, 3, or R. So the opposite. Now we have a name for what we call these two molecules. So two molecules that are non-superimposable mirror images are known as enantiomers. And so these two molecules that we just drew this was S, this one was R. These two molecules would be known as enantiomers. Now, how does this incorporate into the name of a molecule? So here's an example. We know that this molecule would be 2-bromo-pentane. But we need to distinguish it from the other 2-bromopentane because this center here is chiral. Again, we can assign our priority. I'm just going to go ahead and do that, but that's something that right now you might want to pause the video and see if you can do that successfully. Bromine has highest atomic number. That hydrogen that's not drawn in but pointing back is lowest. And then the 3 carbons over here have higher priority than the 1 over here. And so our arrow goes clockwise. And we would call this R2-bromopentane. All right, so these have all been examples where we have one chiral center. What happens when we have multiple chiral centers? So here's 2,3-dibromopentane. And we're going to start with one of the isomers. Again, pause the video, take a couple minutes, and see if you can determine these as R and S. We find the first one is R, and the second one is R. So if we were naming this molecule, because we have multiple chiral centers now, when we put that R or S out in front of the name, we need a number with it so we know which center it's talking about. So this would be 2R, 3R. All of your R and S go in parentheses out at the front of the name, and then the name of the molecule, 2,3-dibromopentane. But how many other stereoisomers exist for 2,3-dibromopentane? So when we only had one chiral center, there were 2 possible isomers. But when we have 2 chiral centers, it's going to double. And we have 4 possible isomers. The one on the right here is 2R3S, 2,3-dibromopentane. On the bottom left, we have 2S3R. And finally, we have 2S3S, 2,3-dibromopentane. So what is the relationship of these pairs, or of all 4 of these molecules? Because they're not all enantiomers. Enantiomers only exist when we have mirror images. Fortunately, that can actually be pretty easy to identify. How do we identify that? Well, we only get mirror images when all of the chiral centers get reversed. So all of the R's become S's, or all of the S's become R's. So when we go from 2R, 3R to 2S, 3S, we've changed all of our chiral centers. So those would be considered enantiomers. Same thing this way, 2S, 3R and 2R, 3S. We've reversed all of our stereocenters, so those are also enantiomers. But what's the relationship of 2R, 3R and 2R, 3S? Here we've only changed one stereocenter. So these are what are known as diastereomers. And I'll define that on the next slide. But any of these pairs that I'm connecting with this light bluish colored line are what we would call diastereomers. So diastereomers are stereoisomers, not mirror images, and not superimposable. And usually the easiest way to identify them is to have a diastereomer. There has to be more than one chiral center. In addition, we find that one center, or at least one center, is inverted, but also at least one center is not inverted. So this is one of those things that will require a lot of practice. And the more practice you can do here, the better. I mean, we say that for everything, but that's even more true here. I just want to finish this section with two other sort of quick definitions, but things that we should be aware of. The first one is what we call a meso compound. So a meso compound is an achiral molecule. So the entire molecule is not chiral. If you put it into a polarimeter, it won't rotate the light at all. But what makes a meso compound special is that it contains at least two chiral centers. And an internal plane of symmetry. So the following molecule has two chiral centers in it. This is chiral. This is also chiral. But what happens if I draw a mirror image of this molecule? So here's the mirror image. And what do you see about that molecule? Well, they're exactly the same. And the reason that that happens is the molecule is symmetric. We have an internal plane of symmetry right within that molecule. All right, the last piece I want you to look at before I send you off to do some practice is to look at what we call a Fischer projection. And the only reason I bring up Fischer projections is personally I hate them. I think they're awful to work with. But biochemists still like them, and a lot of you will likely take biochemistry in the future. So Fischer projections look like this in the simplest sense. And what this represents is the two groups to the side are pointing forward, and the other two groups are both pointing back. And we see these a lot in biochemistry when we work with sugars. This is actually the most common way that sugars are drawn. So at this point, you should go and look at your next in-class exercise. And this is in-class exercise number 6, labeled chirality. And it's going to give you some practice working with these kinds of things.